Hi there. What we're going to work on in this video is how to calculate the equation of a horizontal asymptote, which is also known as calculating the limit of a function as we approach infinity. So here's how we're going to do this. We're going to look at the denominator of our rational function, and we're going to find the term that has the variable with the biggest exponent in it. Now, if you look at this example and this example, they both only have one term. But let's even say if this said like plus 1, and maybe if this said, and you don't have to write this down, but n squared plus, maybe 3n. What we can see here is this is the term that has the variable to the biggest degree. So that's what we will be using. On the last example, you can see we have 3n squared plus 1, so we will be using n squared. So what we're going to do is we're going to take that value from our denominator and divide it into each and every term in both the numerator and denominator of our rational function. So we have the limit as n approaches infinity of 3n over n plus 6 over n, all divided by n over n. And now what we'll do is we'll reduce wherever we can. So n divided by n, that reduces to 1. Right here we have n divided by n, also reducing to 1. So I'm going to do a little rewrite, and later on you probably won't have to write this so many times, but for now it's good to do. We are left with 3 plus 6 over n, all divided by 1. So now I want you to think about this. If n is approaching infinity, if we were to put, say, a 1 here, this would be 6 over 1. But let's put a bigger number in here, like 10. Now it's 0.6. If we put 100 in there, it's 0.06. If we put 1,000 in there, this becomes 0.006. So as n gets bigger and approaches infinity, the value of this fraction right here gets smaller and smaller and smaller and will approach 0. So what we really have here is this. 3 plus a value that will approach 0 as we put bigger and bigger numbers here over 1. So our limit is 3, which means all this work means that we will have a horizontal asymptote at y equals 3. So we're going to do the same exact thing for the next problem. We're going to use a little logic like we did for this one. So we're going to divide n cubed into each and every term. So the limit as n approaches infinity, and now we'll have n squared over n cubed minus 3n over n cubed plus 4 over n cubed, all divided by n cubed over n cubed. Now, if we look at this, n squared over n cubed, oops, I went like a different color there, those will reduce to be 1 over n. The second term will be 3 over n squared. The third term will not reduce. And the fourth term will be n cubed over n cubed, which reduces to 1. I'm going to do a little rewrite just so we can kind of clear this up a little bit, clean it up a little bit. So we have 1 over n, minus 3 over n squared plus 4 over n cubed. And that's all divided by 1, which we all know we don't need that there. So, as we just learned, when we have a number over infinity, it really approaches 0 and becomes nothing. So 1 over infinity here, this fraction will approach 0. Minus 3 over infinity squared will actually approach 0 even faster. Plus 4 over infinity cubed will approach 0 as well. So what we have here is a limit of 0 minus 0 plus 0 over 1, which means our limit is approaching 0. So we will have an horizontal asymptote at y equals 0. Now we have one more way that this can land. We have 2n cubed, 8 plus 8n plus 15 over 3n squared plus 1. So once again, we're taking our limit as n approaches infinity. And now we will divide everything by n squared. So we'll have 2n cubed over n squared. By the way, you're probably thinking, do I have to write this? What if I can do it in my head? Guess what? You need to write it. Plus 15 over n squared. All divided by, and now 3n squared over n squared. Plus 1 over n squared. So we will go ahead and reduce, and what you'll see here is we have n cubed over n squared, which leaves us with just 2n. Right here, we'll be left with 8 over n to the first. We cannot reduce this one. Here, the n squareds cancel each other out. And our last fraction we can't reduce. So let's think about the logic that we used before. Actually, let's do a rewrite. Let's make sure we really get this, because this is a very important topic. So we now have the limit as n approaches infinity of 2n plus 8 over n plus 15 over n squared all over 3 plus 1 over n squared. And if you recall on the previous problems, when we substituted the infinity in here in our denominator, 8 over a very big number approaches 0. 15 over a big number squared approaches 0. And in the denominator, we have 1 over n squared, which would also approach 0. So what we're left with is 2n over 3. Well, let me ask you, what happens when we put bigger and bigger and bigger numbers here? We have 2 times bigger numbers, bigger numbers, bigger numbers. That will approach infinity. So we have infinity plus nothing over 3, which is infinity. So our function does not have a limit. So we won't have a horizontal asymptote. Our function will do something like this. So this can be summed up with 3 generalizations. So let's take a look. And you can refer back to what we just did. If the degree of the numerator is greater than the degree of the denominator, well, that's this one right here, then the limit does not exist when n approaches infinity. If the degree of the numerator is less than the degree of the denominator, well, that's this one right here, then the limit as n approaches infinity will be 0. And if the degree of the numerator is equal to the degree of the denominator, then the limit as n approaches infinity will be the ratio of the lead coefficients. So this is 3n over 1n, so 3 over 1, which we got right here to be 3. So you definitely, I would say, should memorize these rules, but you must be able to show me how you got it as we did in those first 3 problems. Okay? So let's take a look at what we have here. Now we're going to talk about vertical asymptotes. And I want you to, we're going to give ourselves a vertical asymptote at -2. Oops. X equals -2, sorry. This is x equals -2. Let's do one over here at 3. So x equals 3. I'm going to show you the different ways that our functions can act and what can happen as we approach these vertical asymptotes. So I've got another vertical asymptote at x equals -2, and I guess I'll do another one at 3. So 2 of them are at x equals -2, and 2 of them are at x equals 3. And I'm just going to assume we have horizontal asymptotes at 0. So these are the 4 ways that our function can act. So we can have a function that from the left and the right of the asymptote, they're both going up. We can have a function that when they approach the asymptote from the left and the right, they're both going down. Or we can have a function where one side's going up Well, one side is going down, or vice versa. One side's going down, and the other side is going up. So, I'm going to start to talk about limits. This is going to be a very big topic in calculus. What we would say about this function, we have to think about the behavior of the function as it approaches this asymptote. So we would say this: the limit as x approaches -2 of this function is infinity. The reason that the limit is infinity is because both the left and the right, approaching from the left and the right of the asymptote, this function is increasing. It's going up. This is what we're looking at, this behavior right here. So in a similar manner, we can look at our red asymptote here and see from the left, this is going down. From the right, this is going down, which means the limit as x approaches 3 from the left and the right of this function is negative infinity, because they're both going down. Now the third one, they're going in different directions. So because one side is going up, and as we approach from the other side it's going down, we will say this. We will say the limit as x approaches -2 of the function is undefined. We'll also be saying things that the limit does not exist. Okay, so you'll hear some more terminology. But I'd like to lay a little foundation for something. This is undefined because, and I know we don't have a lot of room here, from the left, the limit as x approaches -2 from the left, look what I did, I put a little negative there to the right of my -2 of this function is infinity. So all I'm saying is that as the function approaches the asymptote from the left, it's going up, 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 up forever. And the limit as x approaches -2 from the right, or the positive direction, and notice I just put a little plus sign by the 2 of this function, is positive infinity. So what we can say there is the left-sided and right-sided limits are not equal, therefore the limit does not exist. Very similar here with this last one. We would say that the limit, oops, my pen doesn't want to write. The limit as x approaches 3 of this function is undefined. And if we wanted to lay it out a little more, and I'm not going to write this, I'm kind of out of room, we would say that the limit of f of x as x approaches 3 from the left is negative infinity. And the limit of f of x as x approaches 3 from the right is positive infinity. So just the idea that they are not going to the same place, right? One side's going up and one side's going down. We'll be working with slant asymptotes as well. Okay, basically we will have a slant asymptote when we don't have a horizontal asymptote. So we'll get into that a little bit later. When we need it, I'll teach it to you. So why are we doing this? Well, we're going to be graphing rational functions. So when we look at the rational functions, I have this right here. And what I would suggest you do whenever possible, you're going to factor. So we have the difference of squares in our numerator. And then in our denominator, we have x plus 3 and x minus 1. Now you may remember this from last year. The first thing you should check for is POD. What is that? Well, that means point of discontinuity. Okay, point of discontinuity. Basically, that's like one point on our graph that's not there. So that will occur when we have a repeating factor in our numerator and our denominator. So on this particular problem, we have x minus 3 over x minus 3. That's a dead giveaway that we're going to have a point of discontinuity. Here's what we do. We take x minus 1. I'm sorry, did I say? I should have said x minus 1 over x minus 1. X minus 1 equals 0. We solve this little baby equation. And we know when x is 1, we will have a point of discontinuity. Well, where when x equals 1? What's the height? What's the height of that point? What we do is we essentially reduce this to 1 or cross it out. And now we take the 1 and we substitute it into whatever's left for our polynomial function. So we're essentially doing f of 1, 1 plus 1 over 1 plus 3, 2 over 4 is 1/2. 1/2, 1/2. So we will have a point of discontinuity at 1, 1/2. And I'm going to go drop that on my graph right now so I don't forget about it. Okay, so we have a point of discontinuity when x equals 1. At x plus 3, we know x plus 3 cannot be 0. So x plus 3 equals 0. Solve that by subtracting 3 from each side. What we find is we have a vertical asymptote at x equals -3. Oops, I keep hitting that, sorry. So here's our vertical asymptote at x equals -3. Now let's take a look for our horizontal asymptote. We have, now this is what we just did. We're looking for our function. Are we going to have a horizontal asymptote? We have x squared over x squared. What were the rules we just learned? If the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote will be at the ratio of the lead coefficients. So we have a horizontal asymptote at y equals 1. So here is our horizontal asymptote. So, other things that we can do. We can look for our polynomial's constant in the numerator and the constant in the denominator. That will essentially tell us our y-intercept. So -1 over -3 is positive 1/3. So that's going to be right here. Now that's lower than 1/2, so I'm kind of getting the idea that I might have a, oh, so sorry. I did my asymptote in the wrong spot. Jeez. Should have been at x equals 1. Apologize for that. But what I can see is my function is going down, so I have a feeling it's going to go this way, which means this one will probably be up here. You know how I can find out for sure? I can take the limit as x approaches my asymptote, which is at -3 from the left, and I can take my limit as x approaches my -3 from the right. Now, here's what we're going to do. We're going to pick a number to the left of -3, close to -3, but to the left of it. I'm going to pick -4. So what you're going to do, I'm going to write that -4 there so I don't forget it. I'm going to drop a -4 in for each of these x values. All I care about is the sign of these binomials. So if I put a -4 here, I have -4 plus 1, which is a negative, times -4 minus 1, which is also a negative, over -4 plus 3, which is a negative, times -4 minus 1, which is a negative. What that gives me is a positive over a positive, which is positive. Here's what this tells me. This tells me, because this is positive, that the limit of this function as x approaches -3 from the left is positive infinity. So it's going to go up this way. Now, is this a perfect graph, what I just did, that little branch there? No, we can plot some points. But for now, what that's telling me is it's going up as it approaches the asymptote from the left. Now we're going to do the same thing from the right. So we can see, and I'm guessing, I'm not really guessing, I know, that it should be approaching negative infinity. Well, I'm going to put a number in. I'm going to put -2 in. I'm going to do the same thing. So I'm going to look up here. My pen won't write sometimes. -2 plus 1 is a negative, times -2 minus 1 is a negative, over -2 plus 3 is a positive, times -2 minus 1 is a negative. that shakes out to be a positive over a negative, which is a negative. So what that tells me is the limit as x approaches -3 from the right of this function is -infinity. And again, I kind of knew it was going to go down like this. And now I've just confirmed it. So we just did left and right-sided limits. So here's what I'd like you to do. Go ahead and try number 2. Do everything that you can do, and we will check in a bit. Have a great day, everybody.